Hello and welcome to Sparks and Quarks, a podcast all based around physics and engineering, where we're trying to find out more of our respective subjects from each other. I'm joined today, as usual, by Adam. Hello, Adam.
Hello, Dan. How are you doing this
I'm
week?
I'm pretty good, thanks. Yeah, how are you?
Good. Yeah, I'm really good. I'm looking forward to recording this one.
As am I. Yeah, as I say, so I'm trying to find out more. I say trying to find out more because we've done two episodes so far,
We
and I
have.
I think they've gone pretty well. But we have had a few comments from friends and family and a couple of other people about the accuracy of our discussions now, which is fair enough because a lot of the time we look up our subjects, but we are in no way experts on them.
Indeed.
We're not talking about things that we are well versed in. We're talking about things in our field of interest, and so we're not necessarily going to be 100% accurate. But the point of this podcast is to try and explain, I guess, things of interest to people who might not be so well versed in science and engineering. And if it is something that interests you, then please feel free to go out, do your own research, pick us up on our errors, email us. We'll put our email at the end of the podcast. Please do get in contact. And just, yeah, we're trying to just grow knowledge. And I hope that's something we can achieve today as well.
Yeah, I mean, essentially the aim of this podcast is to create discussion around new things that are going on in science, or maybe not even particularly new things, but things that interest us. And
Yeah.
that's the real aim behind this podcast. So we hope you enjoy listening to us having a nice discussion about these topics.
Yeah, absolutely. We're all learning together, although I'm learning very, very slowly.
I think
Which
I am too.
hopefully our audience are learning a little bit faster.
Hopefully.
So Adam, I mean, what have you been getting up to since our last episode? What's been going on?
Well, I haven't really been doing much really. I started reading a new book, which I will come back to a bit later on.
Okay.
Yeah, I've been working a bit, doing odd bits and bobs. Nothing really of interest has been done in my life. How about with you?
Yeah, it's a quiet season. Yeah, I mean, I'm much the same really. I mean, obviously I've got my job every day, and that's going well. I'm currently preparing. I've been looking into apartments out in Denmark. Some of you may know that I'll be working out in Denmark in October,
Lovely.
for as part of my graduate scheme. So looking at sort of apartments in Copenhagen and starting to get an understanding. I've started teaching myself Danish,
Oh,
which I've
nice.
been meaning to do for a while, but really sort of going at it sort of every day now. So I mean I've got 2 months until I go out, so that's well enough to become proficient in a language,
Yeah,
right?
yeah.
Loads of time, loads of time.
I
Uh,
think you've got time just to sort of get the background knowledge in and just get your feet sort of dipped in the pool of the Danish language.
yes, which I'm going to be honest is bloody tricky.
Yeah, I
Is
bet.
Danish.
I tried learning a bit of Swedish a few months back, and it was it was all right. I could sort of pick up the words, but the pronunciation going from English to some any form of Scandinavian language is
Yeah.
pretty hard to get.
Yes, I think, and please, no offence here to if we do have any Scandinavian language speakers or native speakers. But a friend, when I said I was going to learn Danish, described it as speaking Swedish but with a potato in your mouth. Now,
Lovely.
I didn't know what he meant by that, but having sort of, using Duolingo and other kind of online services to kind of hear Danish, I can kind of see where he was coming from.
Yeah.
There is a certain knack to it. Hopefully, something I'll pick up.
Yeah, I'm sure you will. I mean, you're going to be out there for like 6 months, right? So
Yeah,
by the time you come back, you're going to be coming back and wanting to speak to all your friends in Danish, and they're going to be like, "What the hell are you saying to me?"
I will have forgotten how to speak English, and I will speak
Yep,
only in Danish.
that's how it works, right?
Exactly. Yeah, I'm not that an expert on languages, but I'm pretty sure that's basically how it works.
Yeah. Well, also, we forgot to say last time we
Oh
really wanted to
yes.
talk about this, but for some reason I just forgot, and I didn't actually tell Dan about it until after the episode
I,
was recorded.
I got a message from Adam sort of late in the evening going, "Oh, by the way,
Yeah.
we've got this thing."
Yeah, and this thing is, we had someone from the To Do Discord, the Discord created around Simon Clark's content. Someone from there called Chris made us some beautiful artwork, which was the artwork for the last episode. And she deserves an amazing amount of credit for it. She gave me
Absolutely.
a message and she said, "Hey, would you mind if I did some fan art for you guys?" And I was like, "Yeah, sure, go ahead." This was only after our first episode as
Yeah,
well,
I mean
and
that's pretty good going. One episode and we've already got people making fan art. I mean, what the
yeah,
hell?
I mean, and it's just an absolutely brilliant piece of artwork based around our logo, and we loved it, didn't
It
we?
is. It's amazing. I really want to keep it. Like, can vote to keep that as our artwork?
You know what? For our episodes, I think so. Yeah.
I think so. Yeah, it's really not. You know, we did put a bit of time into like making our own logo, but Chris has sort of blown that out of the water with her interpretation. So thank you very much, Chris. Yeah, it's a really nice bit of artwork, and yeah, we're definitely keeping it. Thank you.
Oh yeah, thank you so much indeed. But anyway, I think you're going to go first this week, Dan, aren't you? Topic one is comes back to you this
Yeah,
week.
topic one back to me, and it's something that so it's not new in the world of engineering, but it is
Okay.
pretty vital to everyday life, and it's something that I'm sure everyone will have used at some point.
Right.
And it's how exactly does GPS work?
Oh, okay. Yeah, I'm really interested to know about this actually.
Yeah, so it is possible that some people won't know what GPS. So GPS is Global Positioning System, and it's the name gives it away. It's a global system whereby anyone with a receiver on the ground can use a series of satellites to identify exactly where they are on the Earth. And this is something that I know. I'm not coming at it completely fresh. I know a little bit about it because it relates closely to my dissertation that I did at university a year ago.
Oh, okay. Interesting.
So, my dissertation was all about takeoff and landing systems for unmanned aerial vehicles. And as part of that, I did research into systems for location, and one of those was GPS. Or rather, I'm going to keep calling it GPS. What it actually is GNSS, which is, he says, trying to remember the actual acronym, Global Navigation Satellite System.
Okay.
So that's the actual Global Navigation Satellite System. GPS is a proprietary system. That is the American GNSS.
Right.
GPS is also called Navstar, and it's owned by America. But there's a number of different ones. There's says trying to find his notes, which he's lost again. Well done, Daniel. Yeah, so GPS, which is Navstar. There's also one called GLONASS, which is a
Okay.
Russian system. Galileo,
Surprise. No.
yeah, I know. Galileo, which is an EU-based system, which isn't truly global at the moment. It should be by 2020.
Okay.
Uh, then there's, I'm pronouncing this right, Baidu, which is a
Baidu.
Chinese system, BEI-DOU.
Okay.
Again, that hopefully by 2020 should be global. And then there are also regional systems. So I'm just going to, every time I say GPS in this episode, I'm actually meaning GNSS, but GPS is easier to remember. So GPS systems, the satellites are in orbit around the globe. Yeah, geostationary orbit, I believe, around the
Yes.
globe.
Or actually, aren't are some of them not in a low polar orbit? I
Ooh,
believe GPS is based around low polar orbit, is it not?
ooh, this is this is the first time. No, not quite the first time when one of us is picking up someone else on the thing. See, this is the trouble. I mean, you'll find there is so much around GPS that you really do have to be pretty much an expert on it to know everything about it.
Yeah.
Um,
You
oh,
know, I'm pretty sure it could actually be to do with a combination of the two. Um, but I think, if I'm right, because you know, back to A-level physics and stuff,
yes.
I'm pretty sure GPS is based around low polar orbit. Please do not rip into me if I got that wrong.
Okay, GPS satellites. GPS satellites are not in geostationary orbit, but rise and set 2 times per day. Now, it doesn't actually say whether that's low polar or not. So, it says here why GPS constellation satellites in such a high orbit. So, GPS satellites are at about 20, yeah, about sort of 15,000 miles above the Earth.
Right.
Now, I don't know what classifies as low polar.
I'm not sure, but it may just be some form of polar orbit then, like a higher polar orbit. I think a low polar orbit is just one that is closer to the ground. So if it's high up relatively, then it could just be classed as a polar orbit.
Yeah,
But I know that a polar orbit is something that rises and sets more than once a day. It rotates around the Earth at a different um, speed to the Earth, so that it's actually moving forwards in rotation with respect to the land, whereas a geostationary orbit, clues in the name, it will stay above the same spot on the Earth.
yes, okay. Yeah, so GPS are not in geostationary, so they are in some sort of orbit, but we don't know whether it's polar orbit or not. I'm going to look into that after the episode. That's really interesting, actually. Um, yes, yeah, GPS or global navigation system satellites are in orbit around the Earth. You've also got regional navigation systems. Um, so these are satellites in geosynchronous orbit around the
Okay.
Earth. So there's two of those. Well, there's two dedicated um, regional systems. Anyway, I think it's called Navic, which is an Indian-based system, and QZSS, which is a Japanese and Asian Oceania kind of region,
Right. Okay.
which are both in development. And I believe Baidu at the moment is regional as opposed to global.
Okay.
As I say, developed to be global. So you can see there's not just one system; you can use multiple systems.
So, what's really the point in having all these systems rather than just one
So,
system?
so because well, I think ultimately it comes down to security,
Ah, okay.
because GPS, obviously we use it day to day for Google Maps or for sat nav in your car, but it's also used for military purposes, guidance of missiles and
Sure.
and other military hardware. So if you're, say for example, that GPS, the American Navstar system, was the only one in existence, and they went to war with Russia, God forbid.
Yeah.
Um,
God forbid, indeed.
yeah, then the Americans could feasibly turn off the Russian access to GPS by changing the codes, and suddenly the Russians wouldn't have any kind of satellite guidance. So obviously, they consider this and they develop their own system, and then EU consider this, develop their own
Okay.
system. So it comes down to sort of geopolitical security, essentially.
Okay, that
Um,
makes a lot of sense,
but
really.
but it also gives sort of civilians or those who have not in a military you know situation. It gives them options of what to use. So I mean, anyone can use civilian GPS. Anyone can use civilian GLONASS, civilian Galileo. Not sure about Baidu, probably. Um, so yeah, it's all about security, but there are there are many, many, many satellites up there because for GPS to function, you need to have direct line of sight with at least four satellites.
Right,
Normally,
okay.
normally you will have, your phone or whatever you're using as a receiver will have direct line of sight with 9, 10, 11, 12 satellites. And the more
Wow.
satellites it's got in sight, the more accurate it will be. But
Okay.
you need four minimum.
Well, that
Um,
just puts into perspective, really, actually, how many satellites there are
oh yeah,
up there, which
there
there
are
are an awful lot.
so many, so
Oh,
so
yeah.
many. Um, But the good thing is there's so much space up there that we can just, well, we can't keep sending them up. It's getting crowded, but that's a discussion for another day.
Oh, yeah, indeed.
Um, so let's get down to actually how GPS works. So as I
Cool.
said, you need direct line of sight with at least four, and that's because GPS receivers conduct what's called trilateration. Now, you may know triangulation. So, for example, if you have a point sort of on a bit of paper, and you do sort of three dots around it, and you
Yep.
draw sort of circles of equal magnitude with each of those 3 points as the center, where those three circles then intersect. If you were in that location, you'd be able to identify where you were because you know the distance from each of those points.
Okay.
Now that's roughly, very very roughly, how GPS works. You then have a fourth satellite so you can correct for satellite clock errors, but I'll come on to that in a moment.
Right, yeah.
Yeah, so the satellites themselves, they broadcast a couple of things. They broadcast a pseudo-random binary sequence, which is just pseudo-random, supposedly random, but nothing is truly random when it's
Sure.
generated.
Yeah.
Binary sequence of ones and zeros. And they transmit that along with the time that it was transmitted,
Yep.
and the location of the satellite was above the Earth when it was transmitted.
Okay.
So the time is very, very accurate. And it has to be very accurate. So accurate that every GPS satellite carries an atomic clock on it, which, this is dangerous. I'm going off what I think is personal knowledge here. I believe it's cesium-127, which is the atomic clock.
I think that sounds about right.
Yeah, but I'm almost certain that someone's going to pick me up on that. But
Potentially.
But it doesn't matter. It's an atomic clock of some sort. So it uses that to broadcast a very, very, very accurate timestamp. So your phone, or whatever you're using, a receiver, then picks up these signals, and it goes, okay, well, this was the location of the satellite when it was broadcast. This was the time. Now, it boils down to speed, distance, time. That,
Yeah.
simple. The speed of light, which is roughly the speed that the signal is being transmitted at. You've got the location of the satellite, and you've got the distance.
Sure.
So you're then able to work out, well, if you can work out the distance you are from one satellite, you've then got, imagine the satellite at the center of a sphere. You know the distance, so that's the distance to the outside of the sphere. So
Yep.
you are located somewhere on that sphere. So you've got yourself on the outside of this big sphere. Now that's great, but you've only got the one, and I'm pretty sure that if you're using GPS, you're probably not just like out in the middle of space. You're somewhere on the Earth.
Yep.
So if you then get another satellite and do exactly the same thing, somewhere those spheres will kind of cross over. And that's great. But then to visualize it, imagine two spheres crossed over. You've then got like a circle, as opposed to like a sphere on the surface you are. You've got a circle. If you keep doing that again and again and again and again, eventually you will get a single point where all of these spheres are crossing over, and that single point is where you are.
Right.
And that's essentially how GPS works. It's
Okay.
by getting lots and lots of spheres, overlaying them on each other, and finding where all of the spheres cross over, and going, okay, I know that I'm this far from this satellite, this far from this satellite, this far from this satellite, therefore I must be here.
Okay. I'm assuming the whole thing with sending a timestamp, is that to do with the sort of rotational mechanics of the satellite, being that it'll move a certain distance in a certain amount of time around the Earth, so you've got to sort of back propagate to the position where it was at that specific timestamp.
I believe that's part of it, but it's so I'm going to try and find the article again now. So this is the trouble. I just as an aside, I'm not currently in my house. I'm currently at a friend's house, and I'm using a portable setup, which is not really that helpful. So I keep losing my place on things a lot more than I would normally. Okay. Yeah, so the reason that it transmits the time that it was transmitted is because you're trying to find your location, which is an unknown. So you've got the satellite's location, which is a known location.
Sure.
And you've got the time it was transmitted, which was a known thing.
Yep.
And you've got the speed at which it was transmitted, which is a known. So and therefore, you've got the time that you receive the signal.
Okay.
So you then have the time of flight of the signal from being transmitted to being received. So you have a time, and then you know the speed, because it's the speed of light.
So then you can find the distance.
Exactly.
Yeah.
And then you find the distance from the satellite to you, and that's where
Got
the trilateration comes into it.
Okay. Makes sense.
Yeah. So I tell you what, it's a lot easier to explain this when you're actually able to visualize it and write things down and look at
Oh
pictures.
yeah, yeah.
So I'll try and find some good sort of example articles that I can put into the show notes. So in a nutshell, that's how GPS works. It's speed, distance, time, very high accurate clocks, and overlapping of signals to pinpoint where you are. Which is a lovely idea, except it has some flaws.
Okay.
You get various errors that creep in to the signal, and whilst tiny in time, because you're using the speed of light, these errors can become sort of bigger, and then if they're happening, every second of every day, the errors can get bigger and bigger and bigger and bigger.
Sure.
So there are various sources of error for GPS signals, and in descending order of magnitude of effects upon the error, the sources are the satellite clock. So, as I said, atomic clock, these clocks have a precision of 1/1000th of a second.
Wow.
They are incredibly accurate. However, our old pal Einstein came up with a theory, which he liked to call general relativity.
Ah, yes, that general relativity boy.
Absolutely. So, general relativity dictates that clocks that are close to masses in space-time, because of space-time being warped, the clocks will then run faster if they are closer to the mass. So that's fine, obviously, when you're on the Earth. However, if you, for example, put an atomic clock into space on a satellite, those clocks can then experience a drift in timing just because of relativistic effects. And so a 1 millisecond drift in accuracy can cause a 300-kilometer positioning error.
Wow.
So...
My lord, I didn't realise it would be that big.
Oh, yeah, because think about it. Think how fast light travels at. And if you're then...
Well, yeah.
If you're then including that in your equation, then, oh boy, you are going to have some massive offsets there. So this is why you have to use a fourth satellite. So whilst you can use trilateration with 3 satellites, you need a fourth to compensate for errors caused by clock drift.
Okay.
So that's one thing. Another source of error is the ionosphere. So the ionosphere is a layer of the atmosphere high above the Earth, which is full of free electrons. So electrons that aren't attached to any atoms or molecules. They're just drifting around, having a grand old time.
Sure. I mean, that's what causes the northern and southern lights, right?
Exactly. That's caused by solar radiation, solar winds kind of passing through the ionosphere and creating wonderful light shows. So the issue is when you're transmitting, electromagnetic waves through the things, they can sometimes be deflected a bit and bounced around by these electrons and charged atoms and charged molecules.
Gotta love electrons.
Oh yeah. Now, that would be fine if, you knew sort of how thick or how dense the electron charge in the ionosphere was. Trouble is that just varies, and we can't predict what it is.
No.
And we can't know for certain. So...
Well, I mean, you'd need a huge, incredible amount of sensors. You'd pretty much have to cover the entire ionosphere just to know the densities of electrons and stuff at different areas, wouldn't you?
Exactly. So you can't predict or estimate the ionosphere density. And the density will affect how fast the signal travels through. It will also... the delay is also affected by how much of the ionosphere the signals pass through. Because if you're standing on the Earth and there is a satellite directly above you, the signal gets beamed straight down, straight through the ionosphere, fine. If, for example, you're standing on the Earth and there is a satellite almost on the horizon, from your point of view, that is transmitting towards you, it's actually transmitting through more of the ionosphere because of the geometry. So that then can cause more delays. So, so a satellite over the horizon will experience a lower delay. Sorry, a satellite directly over the receiver will experience a lower delay than one close to the horizon.
Sure. I mean, going back to what you were saying about if it's almost on the horizon as well, You've also at that point surely got to think of the critical angle at which the signal's coming in at, because
Yes.
it could then just completely reflect off the ionosphere, and then nothing's going to reach you. So at that point, are
Exactly.
you just going to have to move to another GPS, like another satellite? Sorry.
Yeah. Well, this is exactly why, there's so many satellites up there. It's so that
Yeah.
you've got a wide range of things and, wide range of options. Um,
This stuff really makes sense once you start to think about it.
yeah, exactly. And there's I'll come on to it in a minute, but there's a lot of systems to correct this, which are really, really interesting. Um, Another issue is the signal arrival time. So as we said, it's transmitted using an atomic clock, but it's picked up by consumer grade electronics on the ground.
Okay.
So and you're trying to measure the delay in the signal reception. Yeah, in
Yeah.
sort of receiving the signal. So your phone or the receiver or whatever is going to generate an internal bit sequence and then compare that to what it's received and go, okay, well, it's offset by this amount. That corresponds to this length of time. That corresponds to this distance. Therefore, I'm here.
Okay.
Now, consumer grade, global navigation system modules can measure a time difference in bit sequence delay, approximately about 10 nanosecond accuracy,
Okay, that's pretty good.
which is pretty good. So that
Yeah.
translates to an error of about 3 meters. So that's pretty
Okay.
good.
Yeah, that's
Um,
good.
and then you've also got the issue with satellite orbits. So, because as we know, you stick something up in orbit and it'd be great if it just stayed there and, stayed in the same orbit every single time and didn't move and the velocity was constant. That's not quite how space works. Things change up there as much as we don't want them to.
Yeah.
So, although a satellite might transmit, it might say, okay, I am here. That's the satellite saying, I am here using information it was given when it was launched. Like,
Yes.
it's not actually looking at its location and going, okay, I am at this exact location, therefore this is what it is. Transmitting a dumb signal.
Well, else of course, then you'd need another sort of GPS system to
To
track
track
other
the satellites.
satellites.
Exactly, and it just so happens that's what we've done.
Wow. Okay.
But not a satellite, not a space-based system,
Is
a
this
ground-based system.
ground-based? Yes.
Yes, so we
Okay.
have across the globe we have a series of monitoring stations which track all of the GPS and GLONASS and Galileo, all of the satellites, and can say, okay, you are at this location, and
Okay.
it will transmit that up, and it will transmit. The satellites, it'll calculate the orbital deviation of satellites and transmit them back to satellites, and then the satellites will update their internal memory and go, okay, I thought I was here, I'm actually here, cool, I'll use that information instead.
So essentially, what you've done is you've added in an additional constant correction system for the actual satellites as well.
Exactly, exactly. So it's, as you can see, the system is growing. It was just a series of satellites, now it's a series of satellites and a series of base stations.
Sure.
It's huge. And finally, the final system of biggest source of error is multipath. So although ideally you'd have your receiver and there'd be a direct line of sight to the satellite and you receive the signal and voila, there we go. If, for example, you've got your phone and you're using GPS and you're stood next to a big building
Yep.
and you receive the signal, you might be receiving the signal direct from the satellite, but you also might be receiving a slightly reflected signal that's bounced off the building or some trees or the
Sure.
ground.
Yep.
Now, these aren't major sources of error, but because if you think the distance is, maybe you receive two signals from one satellite, you receive one directly into your phone, and you receive one that's travelled an additional 4 meters because it got bounced off the building next to you.
Yep. So that's another incredibly small amount of time on the nanosecond scale.
Exactly. Now, it is tiny, but it is nevertheless a source of error, and it's one of the reasons why GPS doesn't work that well. For example, if you're in a very sort of small street or there's a lot of very tall buildings around you,
Yep.
because there is just so many different multipath routes that the signal gets so noisy that the receiver just gives up and just goes, nope, there's too many different signals, I can't calculate where I am. So
So
that's
is that why, for example, on Google Maps, I'm assuming that's why you get a bigger or smaller circle where you could be around your position?
Yes, exactly. It's because it's estimating where you are, and the more sources of error there are, the bigger the estimations have to be. And so, yeah, as you say, if there's a lot of causes of multipath errors around you, then the estimation is going to have to be much greater.
Sure, yeah.
Exactly. So those are the sources of error, and I've mentioned sort of how the satellite location can be fixed, but there are ways of fixing the other stuff. So, as I said, one of the biggest sources was the ionosphere, the atmospheric effects.
Yeah.
And we could fix this if we knew, the delay being caused by the ionosphere. Okay, that's fine. So what can we do? Well, work backwards. Say, for example, you have a known location on the Earth.
Okay.
You then measure the satellite signal, and so the satellite says, I'm here, this is the time, this is where I think you are.
Okay.
And you go, okay, this is where you think I am, but I know where I am. And then you've got, an offset, and we can say that the biggest source of error is the ionosphere. So we say, okay, well, I expected to receive this signal in 0.1 of a second, for example. I actually received it in 0.11 of a second.
Okay.
Therefore, there is 0.01 seconds delay caused by the ionosphere.
Okay.
That's very roughly kind of how it works.
So is that using some sort of comparison of how the other satellites are comparing? Are they comparing each of their own signals to sort of unify them into more of a dead set position? Because obviously, if you're using the time of transmission and time of receiving the signal as a way to calculate the distance, then surely that's what's determining your position on the Earth. So how is it then going to correct the amount of time? Like, how is it going to know what time to expect if it's using that to calculate the distance, if you know what I mean?
Because the satellite is transmitting its location.
Yes. Yeah.
So if you've got the satellite's location and you've got your location on the Earth, you're then able to work out the distance between you and the satellite without using the time signal whatsoever.
Okay.
So that way, you've then got the distance. If you then take that time signal and go, okay, because of the two knowns I've got, satellite location and my location, you then go, okay, well, the time signal says it should be, 15,000 miles.
Yeah.
I actually know that it's 15,020 miles.
Sure.
So there is a source of error in the time signal that is causing a 20-mile offset.
Okay.
So you go, okay, well, I now know the delay caused by the ionosphere. Now, if you've got this base station, this known location, close enough to your roving receiver, what you're actually wanting to find the location of,
yep,
you can then transmit these ionospheric errors to your roving receiver.
Okay.
Which
Doing
you then
it
use
with
as
one
correction.
Of the base stations, not
Yes,
with,
sorry, I should have been more clear.
Okay.
So it's a base station that then transmits corrections to the roving receiver, which can then correct for ionospheric effects.
Okay, I understand now. Yeah.
Yeah. So that's one of the ways we can get rid of one of the biggest sources of errors. So ionosphere error is now gone. I've already talked about the kind of the base stations around the globe. So these are the base stations that obviously track the satellites. They also act in a similar way. So the system I described is called Differential GPS.
Sure.
The base stations around the globe are satellite-based augmentation systems, and they are similar to Differential GPS because they can also measure ionospheric effects and then transmit that information. So whilst they're good, but then to have the highest accuracy, you'd have to be really close to one of these base stations. And
sure, yeah.
Whilst they cover the Earth, they don't. You might be 50, 100, 300 miles from one. They're not massively close together. Not close enough that you can guarantee that you'll hear it. That you'll be accurate enough in the ionosphere.
Of course.
Yeah, so these series of base stations, you might be close by, but if you're not if you're not that close to them, then you're going to be receiving signal through a different part of the ionosphere, and the information is basically useless. But you still get the satellite orbital corrections, so that's a way of reducing the error. And then the best way of improving your precision and reducing the error is using something called real-time kinematic. Now, when it was first created, and still currently, GPS, there are kind of two systems of GPS. There's what's called the CA code, the Course Acquisition Code, which is used for civilian accuracy and gives you civilian use and gives you an accuracy of about 10 to 15 meters is what's commonly quoted. Often the error is a lot lower than that, but that's kind of roughly what it is.
Right.
There's also what's called the P code, the precision code, and that's what's used for military. And because of the frequency of the signal, it's a much higher frequency, which means that it's a lot shorter wavelength, which means the accuracy is a lot higher. So you can get centimeter level precision.
Okay.
But civilians can't use that because it's an encrypted signal. You need to have a special code that changes daily, I believe. And is obviously reserved for military. However, real-time kinematic kind of manages to get sort of centimeter level precision from the course acquisition code.
Okay.
And this is where we need to go into a bit of kind of radio transmission theory. So when you're transmitting a radio signal, if you're transmitting information in that signal, your signal will be comprised of two parts. It will be comprised of the carrier wave and the kind of the modulated signal, which will be typically a lot lower frequency. So the carrier wave, quite high frequency. If you imagine the wavelength very, very short, it's going up and down, many, 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 many times per second.
Yep.
But then within that, you have your signal, which is kind of encoded in, and that's the information that's normally used. What RTK does is as I said, GPS, you're aligning the pseudo-random binary sequencing of ones and zeros that's transmitted from the satellite by one that's created by your phone. Now, what RTK does, if you think about trying to align two very high-frequency waves, if you sort of put one high-frequency wave over the top of another and then measure the offset in the phase...
Yeah, the phase difference.
Exactly, the phase differential. You're then able to sort of get a very high accuracy on sort of the delay, and then you're able to use that to calculate the difference in location.
Yeah.
Now, I'm going to have to load up the article again here because RTK was something that was confusing even when I'd done a lot of research onto it.
Yeah, I bet.
So I'm going to just read off of here. So much like differential GPS, you've got a base station and then sort of lots of different sort of roving modules, roving receivers. So the base station receives the GPS signal and it measures the delay, or the phase difference, the delay that it's expecting against what it knows.
Okay.
So you're then able to go, okay, well, this is the time. Like, this is very, very, very accurate time in error. So you're able to get a much sort of smaller sort of segment of time that you can then use in your speed distance time calculation.
Sure, yeah.
You're then able to then transmit that phase of the carrier that has been observed to sort of the roving module. Now, if you're interested in this, I recommend you look into it because it is very, very complicated, and it's something that, as I said, despite sort of looking into myself, it's still quite confusing, and I need to do a lot more research into it myself. The point is, by using civilian grade sort of GPS signals, you get 10 to 15 meters accuracy. By using the same signals but by looking at the carrier phase, well, the carrier phase, the wavelength, is 19 centimeters.
Okay.
If you can get sort of a 1% accuracy in aligning those signals, that's 1.9 millimeter accuracy.
Wow. Okay.
So
yeah.
you can get very, very, very high accuracy. I mean, and the great thing is, a couple of years ago, RTK was, it was possible, but you had to spend thousands and thousands of pounds on receivers that could process it and have, all the hardware and the software, the algorithms. Now you can buy RTK kits for a couple of £100.
Wow.
So it's something that the reason I was looking into it is because I was looking at using it on my drone when I built it, and it's something that I want to look into in the future as well. Because if this is where autonomy comes into things. You can then have drones that are automatically landing that are very accurate when sort of delivering parcels to people's houses,
Sure.
whatever you're using them for. So, yeah, this has been a very sort of rough, not necessarily totally accurate description of GPS. I hope it's explained it.
I mean, I'm sure that's explained it beyond a lot of the expectations of people listening, because I mean that's gone into a lot of detail that I'm very happy with how that discussion went in terms of how much we covered with that.
Yeah, I mean, if you are confused, there is so much out there on the net that you can read up on, and again, you can try it out yourself. You can try out GPS on your phones. You can get apps that what's it called? Augmented reality apps, where you can open up your camera, you can point it to the sky, and you can actually see the locations of the GPS satellites.
Yes, I really want to have a go at doing that actually.
That's really good fun actually, because you can see them and you can track them very slowly, but you can track them. And it's just bringing it that much kind of closer to home about this technology that is just in our pockets every day, and we don't really think that much about until it doesn't work, and you go, "Oh my word, why is it not working?"
Yeah, well, I mean, sort of a reason why you don't think about it working is because obviously you can't see it, which is a reason why we don't think about an awful lot of technology. We don't think about what's going on inside of a keyboard or a mouse or any computer or monitor, because you don't have to see what's going on.
Exactly.
But that's why I really love these kinds of discussion, because it just sort of brings things into reality.
And it's something that is used every day, and it's just really, really interesting. And my brain is still wrapping itself around it, despite having done part of my dissertation on it. It's such a sort of broad field of knowledge that you need to read up about.
And there's so much physics that goes into that as well.
Oh yeah, exactly.
There's really an incredible amount of physics going into that technology.
Exactly.
So yeah.
Yeah, so I think that's me done on GPS and how it works. A very sort of rambling explanation, but one that I hope helps.
Brilliant. Okay, so I'm actually going to be talking a bit about quantum mechanics this week, or related to quantum mechanics anyway. And actually, this discussion is going to use Elon Musk's favourite word, nano.
Oh, he loves nanotech.
Oh yeah, nanotech. That thing that's totally real, which
old
he really
Muskie
doesn't believe in, which is just blows my mind, to be honest.
It's a bit
Elon
strange.
Musk, the tech giant that he is, does not believe in nano anything.
Some of the things he's done are very, very clever, but sometimes I do wonder. Anyway, we're not here to talk about Elon Musk, we're here to talk about quantum.
So this has been a bit inspired by the book I'm reading at the moment, which I mentioned earlier, which is In Search of Schrodinger's Cat by John Gribbin, which is all about bringing quantum mechanics into reality. And this is a very real way that quantum mechanics is being used to affect the future of technology, really, at this point. And essentially, my topic is going to be about an emission of light from nanocrystals by using only the effects of quantum tunneling electrons over the barrier between two nanoscale single crystal cubes.
Crikey, okay.
That might have sounded like a load of rambling of really big words, but honestly, give me a chance here, okay? So, I'm going to have to give you a bit of background on what I mean by single crystal,
Yeah,
because
please do.
when you think of crystals, you think, oh, they're like kind of diamond things, all these things that grow out the side of rocks and look all long and pointy and stuff. But really, everything, or everything on a large scale, is made of crystals. So, many solid materials are made up of a structure of atomic crystals which all have a translational symmetry and are arranged in a periodic sense. Now, each single crystal can be thought of as a combination of multiple unit cells, where a unit cell is just a configuration of atoms, with the same shape and orientation. And a solid polycrystalline material is one where multiple crystals are joined together and each crystal is in a different orientation from its neighbor.
Right.
So, is that making any sense? Do you have any questions on that? Because that's a lot of information to take in.
It is. So okay, so it's based. So if I understand it, it's describing a crystal that is
Yeah.
made up of many, many smaller crystals.
Yes, you can think of it that way, or maybe not think of it as a crystal, but think of it as a cell,
Okay.
which has the same shape of atoms combined together in a very specific way, and they're
Right.
all they're all together in the same in a very periodic sense, and all of them have a translational symmetry with each other. And
Okay.
the combination of these unit cells is what makes a single crystal. And then any other material that you see, or any material that you see really, like a metal or a piece of wood or something like that, is most likely going to be lots of these single crystals joined together. But the reason they're not one large crystal is because there'll be a lot of smaller crystals, but they won't have the translational symmetry and won't be arranged in a periodic sense
I
because
see.
they'll have a different orientation from the crystal next to it.
Yeah. Okay. Gotcha.
So that makes sense, yeah?
Yep. Got it.
Okay. So now what's happening in this case is that physicists at the University of California, San Diego have built a device from two single crystals of silver oriented in the same way and connected on only one corner edge with a 1.5 nanometer wide piece of, hang on, I'm probably going to butcher this, polyvinyl pyrroliidone.
Exactly how many letters is that?
Something like 18, something like that, or
Right.
I'm just going to call it PvP.
Yeah.
Okay, PvP for short.
Player versus
So
player. Gotcha.
this is made through advanced chemical solution-based techniques, which allow it to have sort of very precise manufacture, producing completely atomically flat surfaces and very sharp corners. So what I mean by corner edge, connected on only one corner edge, is if you think of how a cuboid.
Mm-hmm.
Now obviously it has vertices at each corner.
Yep.
Now
So
what it's
the
doing is just connecting the edge between two vertices of each one. So it sort of makes a bow tie shape out of the two cuboids.
I see. Okay. So it's not. So it's not like it's not connecting face to face.
No,
So
it's
it's
not.
like it's connecting on the edges between the faces.
That's it, yeah. And that 1.5 nanometer wide piece of PVP is just an insulator that's stopping them from being in contact with each other.
Okay.
Okay, so by connecting electrodes to the nanocrystals of silver, we can apply a voltage. And in order for the current to flow through the insulation, quantum tunneling of electrons across the barrier occurs. Now that's because it's so close together that
Hmm.
the statistics and the probability of an electron being able to tunnel across this distance increases, and that increases as the gap becomes smaller.
Yeah.
Okay, so, or at least that's a very simple explanation of how it works anyway.
Yeah. Of course.
So that occurs, and as the electrons tunnel through the barrier, they're actually transferring energy to something called a surface plasmon polariton,
Right. Is
which
that from Doctor Who? I think I recognise that from at least some kind of sci-fi show.
it sounds like something incredibly sci-fi, but it is a real thing, I assure you.
Right.
And these plasmon polaritons then convert the energy to photons, which is obviously then going to be released as an
Okay.
electromagnetic wave.
Photons being the light particle.
Exactly,
Yeah.
yes.
Cool. Okay.
So the actual plasmon polaritrons are an electromagnetic wave themselves, but they travel along the silver to PvP boundary. So they actually travel along the material,
Okay.
and then they transfer the energy to photons, which get released in a random direction.
Hmm.
Uh, Obviously, to conserve momentum. So
Yeah.
previously, the cuboid crystals had been connected along an entire edge, which gave an efficiency of the light emission of only a few hundredths of a percent.
That's not really very high, is it?
No, it's really not. But obviously, when you're dealing with anything in quantum mechanics, it's so highly probability based that it's hard to get these efficiencies up to anything that's worth using.
Right. Okay.
So by aligning the crystals along the corner edge, this actually has brought the efficiency up to around 2%, which is a lot, like so much higher than what it was before,
Yeah.
a few hundredths of a percent.
That's magnitudes of
Yeah,
you know
it's
of
exactly.
increase.
Which is a really big step forward in this. And obviously, what you're actually trying to do is you're trying to get as much light converted as possible so that it can be used in nanotechnology.
Yeah.
Now, that could be in anything to do with sensors and circuitry and computing chips, that kind of thing. So,
Okay.
what it's actually doing is sort of along the same lines of what you were talking about with technology that will go into GPS. It's creating a high quality optical antenna,
Ah.
which
Okay.
is actually very interesting, seeing as though you had the topic of satellites and
Yeah.
GPS, because we had no idea what we were going to be talking about, as we never do every week.
No.
So there's a bit of layover here. So that's actually what gives the higher efficiency in converting the electrical energy supplied through the voltage through the electrodes to the electromagnetic radiation.
Hmm.
So essentially, what this is doing is it's using quantum effects to create a source of light that uses very small amounts of potential,
Yeah.
which is really cool because, as I say, this can then go into different sensors in nanoscale circuitry and stuff like that. So everything is just going to be made so much smaller, which means that we're going to be a lot more. Okay, how am I going to word this? Let's call it space efficient.
Okay.
So obviously something, and this has happened throughout time. Obviously with laptops, computers, mobile phones, where they've been really big to start with, and obviously the
Yeah.
size of things has just come down and come down and come down.
Hmm.
And that's in, I believe, that progresses along with Moore's law. Is it
Absolutely. Yeah.
Moore's law?
Moore's law, which states that the size of semiconductors gets halved every 2 years.
I think it's 2 years. Yeah.
Yeah, 2 years. Although, as an aside, we're coming to the end of that. We're kind of getting to the point where, coincidentally, quantum tunneling is meaning that we can't halve transistors so much anymore because we start getting the electrons tunneling through.
Exactly. Now that's something that it's restricting existing computer technology, but obviously what this is going to do, because it uses only single crystals on such a small scale, then
Hmm.
it's actually what we're gonna see is as soon as this technology gets a large enough efficiency, then what we're
Yeah.
gonna see is this going into consumer technology, and then the size of computing chips going from the size they are now to a hell of a lot smaller. And obviously we're at the point where we're a bit of a standstill, but then as soon as this comes along, we're going to go from being at a standstill at the size we are now to cutting down
Yeah.
so much that Moore's law may really overall be followed.
Wow. That's something that, yeah, I know various companies have been looking into kind of new forms of transistors that can, like, yeah, still using silicon, but can like carry on with getting smaller and smaller and smaller and avoiding the quantum tunneling effect. But yeah, if we can reduce the size of them by using this, as you said, it's like quantum optical effect. Oh, that'd be very cool.
Exactly. I mean, this is at very, very, very early stages of development. This article that this information came from was only posted a few days ago.
Oh wow, it's really new then.
So I mean, yeah, this is really new stuff, and this is the first time they've actually got and this efficiency is known as very high efficiency in this field, and it's only 2%. Now, what they're trying to do is use different geometries and different materials to try and raise the efficiency by another magnitude. So to get it up to around 20% before it can seriously be thought about being used in some piece of technology.
Yeah,
But to me, I just think this is amazing that we're getting to the point now with technology where we're starting to use quantum mechanical effects to further our our technological knowledge,
yeah.
which
I
is
think
truly amazing.
we are living in the future.
Oh yeah, indeed. But see, it's stuff like this which just makes you think: how are we ever going to progress further than using quantum tunneling effects to make our circuitry smaller? You know?
The thing is, just like we're saying that now, but 20, 30, 40 years ago, like this couldn't even be imagined then. So what kind of effects and phenomena are we going to be using in or researching in like 10, 15, 20 years time that's going to progress things even further than that? Like,
Exactly. Now, this
oh,
is this is the kind of topic. This is why I wanted to talk about this because
yeah.
it's such an eye opener as to how technology has changed over the last 50 years and how
Mm,
technology is going to change even more over the next 50 years again. Like,
yeah.
it's impossible to imagine what technology we're going to have in 50 years' time, which is just truly, truly amazing.
Really is.
But it also sort
Oh,
of makes you think, what have we got now
yeah.
that isn't going to exist anymore then because it's completely
It,
just null and void. Like
yeah,
there's no
exactly.
point in using it. But yeah,
I I
I
love this
think
so much.
I think that's going to be it from me. I know mine was a bit of a shorter topic, but
Well, it's more that I rambled on for so long. Sorry about that.
no, don't be sorry. But honestly, I just wanted to have that little short discussion about that because it was something that really blew my mind,
Yeah,
and I really wanted to embrace the whole Quarks thing this year or this week
yeah. That's a good shout.
with the name, you know,
Yeah,
delve a bit more into nano quantum stuff, you know, all the real interesting physics that is well just so incredibly interesting, but also so incredibly mind blowing as well, and
exactly.
extremely hard to get your head around.
I'm. You're going to put this in the show notes, and I am going to have to just like read through the article because that really truly truly fascinates me. I'm definitely going to read up on that.
Yeah,
I'm gonna have.
do. And also, if you are interested in more of the physics behind it, because obviously the physics it's not easy to understand,
No.
um, but there will be the paper that this article was based off linked to the article, and the link to that will then be in the show notes. So you can have a read of the paper if you like. You may have to have a university VPN or be on some university network to be able to access it without having to pay, but not for the article, but for the paper.
Yeah.
So yeah, it's a very interesting one, but a very complex one.
But that's what I love. I like getting my teeth into the nitty gritty and trying to work out exactly how something works.
Oh
This is what
yeah,
I love. This is what I love about engineering and science and physics and like just you can dive so deeply into something and you can scratch the surface and you go, okay, well, this part interests me, and you can end up going. You fall down a rabbit hole essentially of trying to work out exactly how something works and why it works and the history of it and the different effects that come into play. And
I mean, it's just like from the amount of questions I asked you about GPS, it's kind of like there are so many implications for pretty much all technology
yeah,
that that as soon as you start to follow one, you can be diving into a rabbit hole for so long, and then you come back and then you're like, oh, okay, I've only covered one of these main implications.
yeah,
Now on to the next one. And
exactly.
then you can be in a rabbit hole again. It's something that really blows my mind about science, and like you said about engineering. This is really why it's so interesting.
Yeah, exactly. And we'll put up all of the kind of the articles and the pages and info that we're reading onto the show notes. The only thing I don't think I can put onto the show notes is my dissertation. I will see. I'll ask if I can. I don't know from like a plagiarism point of view or from a publishing point of view the
Yeah,
difficulties of that. I will see if it's possible, and if it is, I'll upload it somewhere so people can have a read if they fancy.
indeed.
Because as I said, certainly with the GPS stuff, visualizing it is probably going to be a lot easier than me explaining it.
I mean, I'm sure there's so many good videos on how GPS works
Oh,
on
absolutely.
YouTube and stuff like that as well. So
Yeah,
if you're interested in sort of furthering knowledge and stuff like that, just give it a search on YouTube. There's going to be so many videos that will help you out and sort of explain things probably in a much better way than either of us have explained both of our topics.
exactly.
So yeah, although you might not be able to find my topic on YouTube because that's a fairly new one and a fairly complex one.
Yeah. Maybe we should get Simon to do a video about it.
Well, yeah, I'm not really sure if quantum is Simon's field, but
Quantum fields. Hey.
hey. Okay, so I think that's going to be it from us
I
for
think
this
so.
week.
Yeah, I mean, what? Very briefly, what have we talked about? I mean, I covered sort of how GPS works, sort of, its accuracy, its sources of error, and kind of what systems we've introduced. And it turns out that it's not just a series of satellites; it's satellites and orbital corrections and tracking and all sorts,
And a whole lot of physics.
and a whole lot of physics.
Indeed. Yeah, and I've spoken about obviously the nano and the quantum and the effects of quantum tunneling electrons to produce light through different geometries of single crystals and all that fun big scientific words. Yeah.
Oh, well, I think this has been maybe slightly rambling from me, but hopefully an informative episode.
Hopefully informative, yeah. I'm
yeah.
sure it is.
Oh, yeah.
Anyway. Thank you for joining us for our brief delve into the world of quantum effects and positioning triumphs. If you're interested in either of the topics we've discussed, the links will be in the show notes.
Alternatively, if you'd like to contact us, our email is sparksquarks@gmail.com. Comments, corrections, and fan art gratefully received. That's it from us. See you next time.